about PDEs and their solution in weather forecasting. And for the second session, we're now going to move on to look at medical imaging and visualization in medical imaging. We have 3 talks with lunch in the middle. Okay, introduce our first speaker. Working. So our first speaker is Arridge, who heads up UCL, looking at many aspects of medical imaging, and he's going to tell us about the regularizations.
Does this?
Ready, Simon? Good. Excellent. Right.
Does that work? Great. Thanks, Chris, and thanks for the organisers inviting me here. This bit of a change of topic. I'm going to just give a little bit of a review of some methods in regularisation for medical imaging, and of course, especially in geometry, but actually even slightly more specialised. I could have put in this title what we call joint image reconstruction, which I'll explain. So I'm going to really limit myself to that topic. So I'll introduce the topic, and then main thing I want to explain is the connection between a regularization of an inverse problem and in a variational form, and then if you take the Euler-Lagrange equation of that, you get, in many cases, a diffusion equation. And then I will also talk, although it's not quite the title of this workshop, it's because there is also a different way of interpreting things in terms of joint statistics. Okay, so let me just proceed. So so the main thing I want to concentrate on is what's called multimodality imaging. So if you're not extremely familiar with medical imaging, you may well know that there are established techniques in hospitals, CT, X-ray CT, based on the work of Hansfield and McCormack, who won the Nobel Prize, I think it was 40 years ago this year, or MR, which also won the Nobel Prize more recently. Very different modalities. This is looking at soft tissue, this is mainly looking at hard tissue, but there are also these methods, 2 examples, positron emission tomography, single photon emission computed tomography. These are what are called functional imaging methods, which in both of these cases they image the concentration of an injected tracer, which is mildly radioactive, in this case emitting positrons, in this case emitting gamma rays. So I won't go through the details of how these are done, but if you look in the modern trend of multimodality imaging is to somehow put these things together and get complementary information. So, for example, here you see in an image of a mouse, you have this comes from MRI. You get a lot of structural information differentiating soft tissues, and the PET you get this hotspots representing where the tracer has been taken up, which in this case is representing activation in the brain, the burning of oxygen, if you like. And then this is the simplest way. You just sort of put color on top, and you get this joint image here. And this similar, this is a human, looking at chest, and in PET and in SPECT. So when you look at this mathematically, we normally consider a variational form. It means that you want a maximum likelihood solution, or one can consider a maximum likelihood solution. That's the model that the solution whose forward projection best fits the data. But we have more than one type of data, so we need to think about scaling them. We also use regularization in the Bayesian framework as interpreted as a prior, so they also need to be somehow scaled to what's the quantitative similarity, the quantitative way of putting together the priors from completely different physical dimensional units. should you choose one image and as known and use it as a prior for others, or should we treat both as unknown and sort of alternate between them in some way? And here's just a partial list that's taken from a special issue of inverse problems, which we recently did. So Petamara is an example I showed in that slide. This is basically two linear inverse problems. Ultrasound and what's called photoacoustic tomography are both based on acoustics, but are nonlinear. So one has to solve a joint nonlinear problem. Then there's multispectral CT, where you have multiple energy windows, sometimes 4, sometimes as many as 100, which you can somehow, one interpretation of which is an extra dimension of space, so 3D in space plus one spectral domain, making it 4-dimensional. Usually treated as a linear problem, but without going into details, it's actually a nonlinear problem, because it's the negative log of the sum of exponentials, which is nonlinear. Something called multiparametric MR, or also known as MR fingerprinting. There are multiple nonlinear channels. And then some other modalities here. And not just limited, by the way, to medical imaging, with very similar ideas developed in geophysics, where one often has to acoustic measurements and electrical measurements, for example, looking at the structure of the Earth. Okay, so what does that mean mathematically? Well, let's call the two modalities 1 and 2 and sort of color code them for ease. So we have an image U mapped through an operator AU to data GU. This is the space of this image, and this is the space of this data. And another modality here. So if you ignore the coupling, you have a likelihood function, which is essentially the data fitting, or the probability of this candidate function U matching this data GU. And in the maximum likelihood idea, you maximize this likelihood, which is equivalent to minimizing the negative log. So these are all decoupled, so we can just treat these separate, and that's what was showed in the first slide. They're just separately, and then they're just fused together in a data presentation way. Or we can consider it as a combined model, so we stack these operators, stack the solution, and stack the data. And then each one may be linear, non-linear, weakly ill-posed, or in some cases well-posed, or strongly ill-posed. So the idea in the joint reconstruction is that we define a joint maximum a posteriori estimate, which we write as this. So we want to minimize over both images U and V the negative log of this joint probability of obtaining U of UV given the data GU and GV. Now we can write, if we ignore for this moment the joint correlation of the data, that's usually reasonable. Of course, in practice, there may be correlation in the likelihoods, but let's assume that the likelihoods are uncorrelated, and this negative log posterior is the sum of the two likelihoods, but we also include this prior term, depends on both functions, U and V. So we'll call this the joint regularization, or negative joint prior. And then another framework is that we sometimes consider one of these to be well posed. So for example, an MRI with complete data is just an inverse Fourier transform, so it's very well posed. So we can reconstruct an MRI very well. So let's say that's V, we've reconstructed it well. So now we'd say that we have just the likelihood of the other modality U, and the prior will now be a conditional prior, U conditioned on V. And so when we do variational methods, we start with a descent method. So we do an iterative update of the current state with a step length times an update direction, which is based on the negative gradient of the likelihood. So in the steepest descent direction, you'd have the negative gradient of the likelihood plus the negative gradient of the prior. But we may also look for quasi-Newton breadths where we pre-multiply this. You can think of it as a conditioner or as a Newton-like step with to give us second order optimization. But a modern trend is, rather than using these classical optimizations, it's sometimes useful to split into two steps: a likelihood update just dependent on the gradient of the likelihood, and then a kind of step which improves this estimate based on the previous estimate and the data, sort of what we call an image processing step, or in variational methods usually a proximal step. So in general, this can be some kind of image enhancement step which is not explicitly derived as a variation of a function. So if this prior is a functional, this image processing step can be written as this evolution by some operator L. This would be the Euler-Lagrange equation of the prior. But you could replace it with any kind of image enhancement step, like a denoiser or median filters. And under certain conditions, these will still have a property of converging to a solution. The disadvantage of this generalized setting is that it loses its Bayesian interpretations. In other words, we can derive the gradient step or the update step without being able to interpret it as the variation of a prior. And then a couple of other sort of key ideas used in developing regularizers. In the discrete setting, we have this idea of a Markov random field. We say that the prior is dependent on the local neighborhood of a given pixel. So if ui is a pixel in image u, then in some neighborhood, we look at the differences between the values, and we attach some kind of weighting to them, which we come to, and to generalize slightly, raise it to power p. Then we can take the variation of this, it's just the same expression to the power p minus 1. So we see that the update step in this pixel is a weighted sum of the differences to the neighbors to some power. For example, if we just take the p2, we have a quadratic expression, and therefore we can write this prior in this inner product form, u with some operator lu, well, in discrete setting a matrix, and the components of this matrix are just these weights wi if j not equal to I, or the negative sum of the off-diagonal elements on the diagonal. So this prior is a kind of generalized Laplacian because it will have any constant function in its kernel. So for example, if you only use 4 connected neighbors and we use a weighting 1, we just obtain the discrete estimate of the Laplacian operator itself. But more generally, if we extend this neighborhood e.g. to the total image, we have what's called the graph Laplacian. And in between this, we take some neighborhood, some local graph Laplacian or a patch-based approach. So in this, when we want to use one image as a prior for the other, the sort of approach we use, what we call it one-sided prior, is that we just try to design these weightings to reflect the influence of V on U. And because we're talking, this is a workshop about geometric methods, obviously what we are going to try to do is to exploit the geometry of U, the geometry of V to influence the conditional prior for U. That's the idea in general. And then one more key component is this idea of sparsity. So let's say now we generalize a bit and we say we have a transformation under some operator E, which we'll call an encoder. And if it's available, the corresponding decoder, that may be the inverse, or it might be the adjoint, or it might be just an approximation of the inverse. So we now transport to some latent domain, psi. And the idea would be that under this transformation, the image is mostly sparse. So that prototypical example is the wavelet transform that's used for compression of images on a daily basis. When you take a picture with your phone and then you email it, you don't email a million by a million, a million pixel values. You get a much smaller file because it's been transformed into wavelets, and then most of the wavelets are set to 0. And so the simplest way to talk about sparsity is to just count the number of non-zeros, which would be the 0 norm of psi. But in the variational setting, this optimization is highly non-convex. So it's usually replaced by L1 non-convex relaxation, which is non-smooth but convex. So the key transform possibility are finite differences. Just look at the gradient. So in other words, your sparsity represents that you're counting the number of edges in an image and ignoring the constant regions. Wavelets, I mentioned, or generalized kernels coming from machine learning, or popular is to use neural networks, where we talk about a variational encoder and decoder, where you learn this encoding in this mixture of affine and nonlinear layers. So then the typical inverse problem, or what's called the synthesis approach, says we're now optimizing for the parameters psi. Our prior constraint is that they should have a low value in the 1 norm. That would be the 0 norm ideally, but that would then, to make this convex, we put the 1 norm. And we say that the decoding of that through the forward operator should match the data under some fitting function D. And so now when we're dealing with joint images, we just need to find a meaning for joint sparsity. And an alternative, which I won't have time to discuss, is this idea of low rank. So we say that the image in some transform domain is of low rank. But that's a global estimate of the image rather than a local. And then a key tool is regularization functions, typically defined in some way like this. So this is using the gradient as the sparsifying transform. So you could replace this with a wavelet transform or some other sparsity transform. If we take the norm of this and then we apply a local function, it's just a function of one variable, integrate over the image, then this is differentiable, and this is where this diffusion format comes from. So now the first variation of this functional looks like a diffusion equation, the divergence of a scalar diffusivity function, which takes this form. We just differentiate this function and divide by the gradient, applied to the gradient itself. So for example, commonly used one is total variation, so you just have the 1 norm itself, so psi is just the identity function. So the derivative is just constant divided by gradient u. So this diffusivity, this means that the flow in the image is reduced when the gradient of the image is maximal. But of course this leads to a problem at 0. It's non-differentiable at 0. So we can deal with that using the splitting methods. And for example, a proximal operator for TV is quite easy to define. But there's typically used some smooth variations of this thing. So something called smooth total variation, or the pronomatic function. There's a long list of functionals which have slightly different properties that you can construct, but they all give rise to these different diffusivities, and they're all solved by just diffusive flow with a different spatially varying diffusivity. We can generalize that a bit, as I say, without it being the variational functional form. So this approach of Weikert used a tensor approach where we define something called a structure tensor, which is based on the outer product of the gradient with its transpose, and then smooth to get some stability. So if you take the eigensystem of this, it becomes what's called an edge-enhancing diffusive approach. The idea is now that we decompose this, so this V1 becomes approximately the tangential direction and approximately the normal direction. And then, but you adjust these functions gamma according to choice. Sorry, V1 is the normal direction, and V2 is the tangent direction. So a typical approach is to make this normal derivative something which becomes small when the gradient is large and becomes 1 when the gradient approaches 0, and the tangential is always 1. So this construction produces a flow which smooths in the tangent to level sets, but inhibits smoothing across level sets, which in other words, it preserves edges. That's why it's called edge-enhancing diffusion. So maybe I should speed up. I think I might skip this, some more details of that anisotropic filtering. And let's just mention another approach based on statistics. You can also define a joint functional by looking at something such as this joint entropy, just defined by the joint probability of U and V negative and integrated over both images. So this produces the idea then is that the regularization is such that we want to reconstruct an image which has the minimum joint entropy. And that will be accomplished if the joint probability density is sparse. This can be made computationally efficient using Parson kernel density estimators for the joint probability distribution, but it's very, very non-convex. Just to show you an example here, so if we take this as a ground truth MRI image and a candidate PET image under different circumstances, so if you look at now if we just plot the joint distribution of pixels in this image and each of these images, so the PET image is in the horizontal axis and the MR in the vertical axis. So, for example, look at this one where we have a sort of ideal ground truth. We see that each pixel here belongs to one of 3 classes in this together, which are well separated. So the joint histogram is quite sparse. If there's some partial volume effect due to blurring, which occurs because a PET has an inherently lower dimension, lower resolution, then you get a streaking in this direction. And if there's some other selection of this reconstruction, so that, for example, these 2 gray scales, this light and gray matter, are merged, then these have the same distributions. They have the same density on this axis, but they still have a separate density on this axis. Using this approach, these are results from a paper in 2011, I think, where we reconstruct this as the separately reconstructed PET image and then the jointly reconstructed with different strengths of the joint prior. But because we're talking mainly about geometric regularization, I won't talk much more about this. And maybe I'll skip that one. So let's for the last part, let's talk about how this how the geometry of one image can be incorporated into the prior for another image. So let's go back to this formulation where we take the sparsifying transform as the gradient. And we just start with a quadratic functional for this small psi. This is a work from the Carpio group in 1999. Now we modify this norm to include this tensor field, which is dependent on the image V. So this can be written by, we can do decomposition of this metric into this form where L is a upper triangular matrix. And that can be written by expressing it as inner product as this rotated gradient or divergence tilde on gradient U and a matrix, local matrix lambda. So what do those consist of? So the suggestion in this paper is we write B in this form here. You take the normal and the tangent directions of this of the image V to produce U hat and tau hat. And then we write this construction here. So what you can see from here is that this can be written as the outer product of the tangents, the outer product of the normals with some weighting gamma. So if gamma was a 1, this would just be identity. If gamma is 0, it's purely the tangential field. But in general, we write it as a rotation, a diagonal matrix, and the anti-rotation. This is what defines this matrix L. So the rotation is just given by the direction, the local gauge coordinates, nu hat and tau hat, which is a rotation by theta according to the direction v hat. And then lambda is similar to the edge-enhancing directional flow. We construct this to be an anisotropy matrix where this one, this we keep 1, so we always have the tangential flow, and we put this factor here between 0 and 1 to inhibit the normal flow. But the normal flow is now dependent on this image V and not on the self-image U. So at the end of the day, we get this diffusive flow where instead of the scalar diffusivity, we have now a tensor diffusivity given by a rotation into the local gauge coordinates, a scaling between the normal and the tangent, and a rotation back. And then we generalize this a little bit by putting this function back psi. So now we take this same construction, but we apply this local functional here. So now we get this slightly more complex construction. We can write it a number of ways, but if we write it in this way, we get the same rotation. We split this diagonal operator in half, so it's symmetric. And this part here now depends not just on V, but it depends also on this structure U. So this is something where we're now getting some flow which partially depends on the structure of V and partially depends on U. And then let's look at this a little bit further. Now we look at two images, U and V, and look at the level sets of those. So if this is the level set of one image and the level set of another, the normal direction is perpendicular to the level sets. So what if we define a metric that tries to force the level sets to be parallel? So we can define it a number of ways, but one way is like this. You just take the magnitude of this vector and this vector and the rotation, this angle theta between them. To make it a proper distance, we have to do some manipulation of this function. This is work done by Matthias Ehrhardt in his thesis. And we can write this in terms of some generalized monotonic functions psi and phi, with certain special cases simplifying to other known previous flows. And under this construction, the interesting thing is that we get two flows. We get the flow for U and the flow for V. They both have very similar form. And the flow for U depends on the gradient of U, the rotation that's based on V, and a diffusivity function which depends on U and V. So the other flow, we rotation based on U and the diffusivity based on both of them. And so finally, we'll show a result there. This is for the MRI PET case. So this is a PET image. This is what a PET image looks like. It's rather blurry. MRI, we said, normally looks high resolution, but when we do undersampling in the Fourier space, you get artifacts in the MRI. The undersampling is a useful thing to do if you can, because it accelerates the acquisition. And then we see here some different constructions of TV, joint TV, and then two different versions of this parallel level sets approach. So again, time has run out, so if you want some details of this, I can show you afterwards or refer you to the paper. Okay, so summary, we can define joint reconstruction based on statistics or geometric cross information. We can define it as in a variational form or just as a PDE, which is not a variation of a functional. And the remaining question is how best to combine the statistics and the geometry. Is there a way to look at a geometry-preserving flow that is also producing sparsity in a statistical estimation? And as I briefly mentioned, when we look at the sparsifying transform, in the general setting, we can discuss that as an encoder and a decoder, which is precisely the language that are used these days in neural network approaches. Okay, so I'll stop there. Or I'll just
Thank you very much, Simon. One quick question. Yes.
yeah. Yes. Right. Yeah. Yeah, sure. I think I know what you're talking about. I mean, I didn't have time to talk about all those possible because that's. I wanted to concentrate on geometric methods. That's a slightly more general method, but it's a very interesting approach. But I'm not sure that it's been applied to the joint reconstruction problem, has it? Okay.